Okay, everybody, how are you doing? Good? All right, what's going well? Okay, I'm sorry. Okay. This is what do we have? Two more, right? If I'm not mistaken. Okay. This is our penultimate session where we will be covering new content. And the last time we meet, it'll be an opportunity to review, answer questions. It'll be pretty open-ended, actually, is my plan. Okay? Any questions administratively before we get going? Okay. If you could kind of, yeah, great, awesome. Thank you very much. Okay, so today we go back to beams. How many sessions have we had on beams?
3.
4. This is number 5, and then we will have number 6 on Thursday. Okay? And what have we done with beams, right? We've talked about how to calculate the bending moment and shear force across it. We've learned how to calculate bending stresses across it. We've learned how to calculate transverse shear across it. We've got a general idea of what the forces and the stresses are doing. Today, we're going to talk about displacement, okay, and talk about deflection. How's the beam changing its shape as we go along it? And this topic is, how do you say it? It's pretty key, pretty critical to the wealth of knowledge that you accumulate as a mechanical engineer. Okay? So what we're going to do, we have 3 parts that we'll be covering. First, we're going to derive equations for deflection. And you may be a little bit bored. You're like, oh, a lot of times you point us to a YouTube video, you point us somewhere so that we don't have to do the derivation. In this case, I think it's worth doing the derivation. Okay? Because in this derivation, we're going to see some parallels to things that we've learned about relationships between distributed force across the beam, shear force across the beam, and also bending moment. Okay? We'll then get into how we go about calculating deflections across the beam. So we'll talk a little bit about the process and a little bit about what we need to keep track of. Okay? And then the third part will be an example of using finite element analysis, which we get to do again, all right? This time, though, you're going to be happier, okay? Because we're just going to do it in FreeCAD, okay? And so you don't have to do FreeCAD and then pre-POMAX. Pre-POMAX allows us to get some very powerful images and understanding about what is happening with stresses and deflections, quite frankly. Nonetheless, this is kind of a shortcut, simplified way to do it. Okay? Any questions? Here we go. So, why do we care about deflection? What do you think? Is this too rhetorical of a question? But why would we even care? Deflection of yes, Chris. Not that Chris. Yes, Chris. Yeah, so if something's changing shape, what does that mean? Deflection, yes. It could mean, right, from a high level, from the perspective of your functional requirements, it may mean that it bends so much that it's no longer very useful. Okay. If you're designing a diving board that we can think of as a beam, and it deflects the wrong amount, I mean, first, does it break, right? That's the first question. And so we have the tools to calculate if it's going to break or not with calculating bending stress and transverse shear stress. The next question, though, is does it bend the right amount? And guess what? We can also calculate an effective spring constant using what we're doing today, right? So does it have the right springiness for what we're attempting to do? So we have to meet certain function requirements, right? If this, well, I need to get this thing to work. All right. So if this beam here, right, if the bar, all right, now that's confusing, right, because we call that the bar if you're weightlifting, okay, but it's a beam here. Okay? I mean, it's also a bar, but the load here is transverse, right, with the weights on either end. Right, if that thing bends too much, that's gonna be annoying, okay? If it bends, you know, when one person uses it and then another person uses it and they use it at a different rotated angle, right, that could be annoying too. All right, so you could get it kind of warped in two axes. When I was a grad student, I had an opportunity to do a little bit of. I wasn't really a true consultant, right? This professor I was working with he was the consultant, but I did the grunt work. Okay, and so there was a case where someone got hurt. I don't know the details, but someone got hurt using some type of bar, okay? And so what we had to do is we had to figure out if the bar had the appropriate strength. And we haven't really covered this in the class that much, but in addition, and you'll do more in DMC, a fast way, right, we could put it in a tensile testing machine, right? We could have cut the bar and then try to put that in a tensile testing machine. A bar of that diameter would have required a pretty, in that material, right, that would have required a pretty high force material testing system. But instead what you can do is you can do what's called a hardness test. So he actually had this portable hardness tester, and what it is you put a little ball, okay, over into the material. So you actually put a divot, you like push that bar, or like push that ball into the surface. And then based on, the machine did it automatically, and it was just a portable handheld thing. Based on the amount of deflection that you would have, okay, or how much that ball goes into the material, that gives you an idea of how hard the material is, and you can kind of correlate that hardness to the strength of the material. So, why else? If the material is brittle, okay, you could have failure, right? Or if it's ductile, you could have failure, okay? But you don't want to have too much deflection, and that deflection, of course, is correlated with the stresses involved. And maybe that leads us to this idea: can we go from deflection to stress? So if I'm an observer, okay, of what's happened, okay, if I see something's deflected, can I get an idea of what the profile of the internal stress might have been? So there was another case where there was an issue with a ladder, and there are these like bar protector things that go over ladders. Anyway, I probably shouldn't go into details. There aren't that many ladder companies. But anyway, there was an issue, and there was a part that got seriously deflected. Okay, and so we had to go back and had to figure out what had happened. And all we had was essentially the information about, well, it deflected significantly here, and figure out what the load was that caused that deflection. Okay. All right. And wouldn't it be nice to have a spring constant, right? It's been a little bit of a while since we've talked about spring constants. Okay. And we haven't done it really in the context of beams, not that much at least. We've done it in the context of bars, we've done it in the context of shafts, right, that are twisting. We have a K eta equals torque, right, if it's a shaft that's twisting. In this case, we're going to be looking though at F equals K delta, and we're going to be thinking about displacements along the beam. Okay. We won't do that So and then so that's something we can do. Okay, but another thing that we won't really cover too much today, but if you are interested in how a structure vibrates, okay, you might also want to know what its spring constant is. Did we talk about? I love talking about washing machines. Did we talk about washing machines in this class yet? Okay. Well, I just love this one example. All right, so here's a question for you. And this is going a little bit off of topic, all right? Why is a washing machine, you know, we're talking either side load or top load, right? If I put my hand into the washing machine and I have the basin, right? The rotating basin where the clothes go. Why is that thing, have you ever done this before? Hopefully, right? Have you like touched it? Right? Have you noticed that it's really wishy-washy? Right? It like just moves very freely. Have you also noticed that it spins pretty fast? Okay, so why would it be wishy-washy? Why would it be really easy to push around inside the washing machine cavity? Any ideas? Yes? Okay, damping. Well, is that damping? Is it damping if I'm able to just like, because it like, I mean, there is damping involved, yes, but that's I could have very high stiffness and still have damping, right? It's not very stiff, is my point. Yes.
So that the whole machine doesn't vibrate or
Okay, so if the whole machine doesn't, that's correct. That's correct. It has to do with preventing vibration. Okay, why is that the case? Any ideas why why is it? Why don't I just make it really stiff? If I don't want it to vibrate, shouldn't I just make it like stiffer, stronger, less displacement? What do you think? Okay, Jesse? Costs a lot of money. Okay, good thoughts. Good thoughts. Okay, so has anyone ever had a washing machine delivered that didn't have, when it's shipped, it actually has support structures often put inside? Anyone ever receive one and they forgot to take out the support structures? Yes? What happened? It fell? Like the washing machine actually fell over? Oh my goodness. Okay. Yeah, so we had this happen actually. And it like shook like mad. Okay, it was crazy, right? Okay. So stiff is bad for some reason. But why is stiff bad? Yes.
It's similar to like the guy holding the bar. You want a little give. You want it to stretch a little bit.
Okay.
So it doesn't snap.
Okay. All right. Okay. Yeah. So you want it to be a little bit ductile. Okay. All right.
You don't want the material to fail.
Okay. Yes. But yes, we don't want the material to fail. My question is, why would I make it less stiff? All right. Another question: why can I go over to my big car or my little car, whatever car, all right, and or even a bike? Why in the world would you put a spring? I mean, there's a damper there too, right? But why would you put a low stiffness spring on the fork of a bike? Well, that one's a little bit different. That one has to do with absorbing vibration, right? A little bit. Okay, but you're actually making it less stiff. Okay, if I go over to the side of the car, boom, 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 all right? Like I can make it go up and down. It's less stiff. Okay. It's because something to do with vibration. So that part has come out, right? Do you remember when you took differential equations or calculus? Do you remember mass spring damper systems? Okay. All right, forget the damper part though. Do you remember mass spring systems? All right, the physics professor, he went over there and he's like, hey, look at this. right? I can find its nice resonance. Okay, do you remember this? Okay, or you can do it kind of with a pendulum, right? I can find, yeah, there it is. That's about resonant right there. Okay, do you see that nice little resonance? Feels good. Everyone's happy. All right. Okay, now what if I go slower? Well, it just kind of follows along, right? I'm not 180 degrees out of phase, okay? Or I'm not 90 degrees, yeah, I'm not 100, right? Here I get out of phase. What happens if I go fast? I'm not doing it the best. The displacement actually goes down. Okay, do you remember that? If you looked at these frequency responses, okay, for the mass spring damper systems, there was this like, whoo, shoot up and then come back down. And it goes down as a factor of 100 per decade. Okay? A first order system goes down a factor of 10 per decade. A second order system goes down by a factor of 100 per decade. So what you actually do is you purposely put the resonant frequency really low. Okay, so the resonant frequency is really low. So then what happens is then you go down the curve. Like if you go down, I should just draw this because we're talking stuff. If you look at the frequency, okay, frequency, and this is going to be displacement. We'll call it magnitude of x. All right. What happens is you go up to a resonant frequency, right? And that's what we often call like the omega n or the Fn, right? And then it's like resonating, but actually after you go past that resonance, you get a major decrease in the amount. This is like a ratio of what you put in. Sorry, you can't see that because it's not working. This is a ratio of what you put in and what you get out, all right? So you get out a lot here when you're at the resonant frequency, but then as you keep increasing the frequency for a given amount that you put in, you get less out. Okay? So how does this tune, what are we talking about here? So we're talking about beams, all right? And in some cases, cars can have leaf springs, okay, underneath for the suspension. Yes, they can be, the nice helical springs, but they can also have leaf springs in there. And so that stiffness is tuned to appropriately resist the high vibration, okay, of your wheel as it goes along the street. Okay? And so that you don't feel every little thing, right? I don't have a fancy car, all right? But some people have cars that go up and down, they do all this crazy stuff, right? But you have a general idea that if you're getting a car that's low to the ground and it's meant to be a roadster, right? The stiffness is quite high. Okay? But if you are going for a vehicle, right, that's going to be on the dirt, right, and you have lots of bumps and you're going pretty fast, right, you're going to have lower stiffness in your suspension. Yes, Chris.
So they said that non-helical spring.
Yeah, so when I say a non-helical spring it can be like, yeah, it's like pieces of beam that are put underneath, right? So if you look at some of these vehicles, right, they have these leaf springs in it. Yeah, they're called leaf springs. Look it up. Yeah, not every suspension is made the same way. Okay, and you can some of these you can tighten and loosen as well. Okay, let's go. So that was the interesting part of today. Now, of course, everything we do is interesting. Yeah. All right. So, do you remember we've had conventions where we've gotten together and we've discussed what is positive with beams? Okay. So here we go again. If we have an x, we have a y. Okay, and we have a distributed force, all right, and it's coming up in the positive y direction, we're going to say that's positive. Well, that's a straightforward one. Now, if I have a bar, okay, and I have a force coming out of it. We don't talk about this that much, but we still can. If a beam, right, has an axial load, it's behaving as a bar, right? And we've done combined loading, so you've got this kind of idea, right? And again, if this force is in alignment with the positive vector direction coming out of that surface, we're going to say it's positive. Okay, so positive F when it's in the positive X direction for this particular case. Okay, and then, right, we've also talked about what is positive moment. Okay, and we have the idea that you're making these smiley faces, okay? And that when we take a slice, right, we want to do that, and this would be in the z direction, right, and this is the minus d direction, the way we've drawn things here, right, using the xy. X cross y is going to give us the z. And when we think about shear forces, right, we have, again, a convention that's maybe a little counterintuitive, but if we open to the right, we have V downward, and if we open to the left, we have V upward. Okay, so you're like, duh, I got this. This is boring, all right? But this is just a review. And I guess I've also said that, I've told you the story, right? I was confused about this. Because when I took the class, we were using Crandall, Dahl, and Lardner, and they use the opposite convention for V. Okay, and so when I started teaching the class, I was like, this seems so backward, and it was. We've also talked about how using these different conventions can, how we can account for them in our on an element, right? You saw those Wikipedia shots that I put in that shows, okay, more circle goes this way, more circle goes that way, depending on the convention, right? So, okay, what constraints do you see here? You tell me, what constraints do you see here? Go ahead, you raise your hand, so give it a whack, Federico.
Well, two big supports. Are those constraints?
Yeah, so there are constraints here, all right. These, they're maybe not the ones that we've used before. They're a little bit weirdish, I guess. Okay, this one right here, that we'll call a pin. All right, you see, because it's got a little pivot, so it can't provide moment. All right, so that's like a pin, right? And this one, this is like a roller over here, right? Okay, what other constraint or non-constraints do we see here? Or anyone? Okay. Here, this is what we call free end, right? And this is also called a free end. Okay, so in this case, right, this constraint here, it can provide a force, but no moment. Over here on the free ends, there's no forces, there are no forces, and there are no moments. Okay? And so that's kind of overhang, right? The pin constraint is more what we see here, okay? And we saw it previously here as well, okay? And so they can provide restraining force, but they can't provide a moment. And what is this? This is a fixed wall, which can provide both force and moment as a restraint, okay, or a constraint. And if I put either a roller on this side or a wall on this side, I immediately go, ugh, why did you do that? Because I've over-constrained the system, which we'll talk about next time, right? Remember, if you get a structure and you start adding additional constraints, okay, you have redundancy, you don't need those constraints. And what that means is that you have an indeterminate system, and we have to use both constitutive and equilibrium-based equations. Okay, the elastic curve is what we're going to use to describe the deflection along the beam. Okay, so there are a couple elastic curves right there for us to look at. Okay. Now, curvature is going to go with the sign of the moment. When I mean sign, not the S-I-N-E, but the S-I-G-N, okay? We're just getting a qualitative intuition here. We're going to have equations in a minute, but just a qualitative intuition. So what we're saying is that if the moment, internal moment, is positive, then we have positive curvature upward. And you already kind of know this. We've talked about this multiple times, right? It's like, get a sense of what the deformation is, but we haven't told you what the deformation is. Just get a sense for what that deformation is. And so if I apply a negative moment, right, like this, I get negative curvature. And the way that we look at negative curvature is kind of interesting. The center of the circle, okay, or the semicircle that is formed is below the neutral axis, or below the beam, okay? This is negative curvature, so there's some center right here. And if it's above, right, that's positive curvature. Okay. So you see those center points, the O's. Now, let's take a kind of an additional qualitative idea of what's happening with curvature. If you were given this system, would you be able to construct the shear force and the bending moment diagrams? Yeah, right? Okay. What would you do here, right? You'd probably say, I'm going to have a force going up as a reaction over here, and a force, going up as a reaction over here, and we're going to go across, right? And what are we going to see? We're going to see something like this, right? This force P is going to cause a flip, right? And the internal shear force, right, across it, right, you can see there's nothing happening. There's no distributed force along it. So it's got to stay constant until it gets to this concentrated load, right? This should be familiar. And, right, I could do this multiple ways, right? But one way we know is that dV dx equals m, right? No, I'm sorry. dV dx equals w, and dm dx equals v, right? So you can integrate the v, all right, to get the m, if you so desire. Okay. Now, is m in this case positive or negative across the beam? The internal bending moment. It's positive, right? So based on what we just said, we expect that the curvature is also going to be positive for the beam across it. Okay? And that's what you see. And there's somewhere out there, somewhere way out here, right, you have the center of the circle that's being formed, okay, by this curve. All right, and this is also true with this system, okay? The magnitudes are a little bit different, okay, because we've moved the load over, but once again, we can see that it stays positive, and that means, again, that we're going to have positive curvature. Okay, so we're just getting a qualitative sense of what the deflection should look like. Now, we have, at this point, kind of established that moment and curvature are connected. Shear force can contribute to curvature, but its effect is quite small. Okay? So we normally don't think about shear force unless we're thinking about in with respect to moment. Next, when you take design of mechanical components, you will be able to calculate deflection due to shear force, and you'll see that it's very, very small. What we do, again, is we have some distance along the beam, all right, and we have a bending moment m, and we describe v, okay, so this is a convention that you want to keep in mind. V is positive if it goes upward. So this is actually all negative V. All right, the curvature is positive, but the V, the displacement, okay, of the beam is negative. All right, and what is V? So people are going to ask, what is V? What is V? This is little v. This is not shear force V. Okay, we just showed shear force V over here. All right, confusing, of course. Big V. This is little v. Okay, and we'll try to be clear with that. Okay, so this is negative. Now, we can also think about the radius of curvature. Okay, right? So what is radius of curvature? Well, you remember in calculus, you had 1 over rho, or 1 over the r was equal to the kappa, and the kappa was the curvature. Okay, so yeah, we're going to do a little bit of that in a minute. Okay, but rho is the radius of curvature. Y is the distance from the neutral axis. M is the bending. And let's start with a undeformed beam. Okay, and we're going to put these marks A, B, C, D, E, F on the beam, and we can draw these little cute lines vertically, right? But it's all the same material. Okay, we just have these locations, and then we can look and we can think about what an undeformed element in this beam might look like. So, what is it? Very boring. It's a box. Okay, this is a 2D perspective. We're looking at, it could, since it's an element, right? This is essentially infinitesimally small. Okay, all right. So it could be like a little chunk of the beam. All right, or infinitesimally narrow. All right. So we define that as having some width, delta x. And we have a longitudinal axis going through this. So this is a slice, all right? And then you remember the longitudinal axis or the neutral axis, that was what we would say had zero bending stress, right, along there. And it also has zero extension, okay, zero change in length as these beams bend. We have a distance away from the longitudinal axis or the neutral axis, and we call that distance y. All right, and then we're going to define the length, okay, here at a distance y above the longitudinal axis. In this case, is delta s, which is supposed to be small. All right, this delta s and this delta x are the same, and this will come up a few times. Now, what happens if we deform our elements, okay, our little slice? If we deform our slice, or our beam, okay, we can look at maybe it's this element now deformed, okay, and we go from here to here, right? It gets smaller, and here to here, it might be getting a little bit larger, okay, and there's a row, okay, right here, that we can define, okay, going to the neutral axis or the longitudinal axis, okay, like this. Okay, that's the radius of curvature. And it's sweeping out now a delta theta, right? In this case, we had no delta theta, it was undeformed, right? But now that we've applied some moment and we've bent it a little bit, we have a defined delta theta. Delta x, okay, this distance or the distance that we can think of along the longitudinal axis, has it changed? No, it has not changed. And then we can think of what happens a distance y above the neutral axis, okay, and if y is positive in this case, with a positive m being applied, is this distance from here to here, it's changed, right? It's smaller. Okay, so we now have our delta s, and we'll call that delta s prime. And now we'll just put these bending moments on there as well. Okay, so in this case, where we've got our undeformed beam, okay, and then we deform it, which part of the beam is in compression, which part is in tension?
The top part
But-
is compression.
Top part is in compression, right? Underneath the neutral axis or the longitudinal axis is going to be in tension. Okay. So we have an idea. We know this, right? Right? Sigma is equal to negative my over I. Okay, and so we're still following those relationships. Okay. Now, though, we're going to use geometry to think about how we can think about strain. Okay? So, remember in that previous one, we said there was a delta S, okay, or a delta S prime, right? Say from here to here, or in some narrow slice. Right? Some infinitesimally small, or infinitesimally thin slice, better said, but it's still going through the thickness of the beam. So what we're going to think about here is, what is the strain associated? Is there any strain on the longitudinal axis? Is there any strain along the longitudinal axis, along the beam? No, right? Because it hasn't changed its length. Okay. Is there any stress along that longitudinal axis? Normal stress, right? Not transverse shear stress, but is there any normal stress? Also no. All right? And that's nice, because if you have just normal loading, right? Uniaxial normal loading, you know that sigma is equal to E epsilon. So that is going to fly. All right? That lines up with what we've seen before. Okay, now we have our distance rho, we have our delta thetas. Okay, we have our longitudinal axis, and now we're going to look a little bit more, okay, at what's happening with deformation, and we're going to look at delta S prime, and we're going to think about delta S prime in relation to the original delta S. Remember the delta S? We said when it was undeformed, delta S, okay, is not shown here. Delta S is just delta X. And delta X doesn't change, because delta X is is along the longitudinal axis. Okay, so if we're interested in figuring out the strain, now what is the strain? This strain is a function of Y, but it's not in the Y direction. The strain is in the longitudinal direction. It's in the delta X direction. Okay, it's in the X direction. So that's the strain coming across here. How do we do it? Well, what's the definition of strain? The definition of strain is change in length over initial length. Right? And it just happens that this is a narrow slice, so we've got deltas, and we're doing a difference of deltas. Okay, so the delta S prime, okay, minus the original length over the original length. And then we say we're going to take that down to 0. That means we're just going to make it, really, we're going to say, oh, there was a delta S, it was kind of thin. Now we're going to make it infinitely thin. Okay? What do we know? We know that delta S is equal to delta X. Remember? That's this length right here. And look, rho delta theta. Okay, do you remember this? This may be how you figure out the perimeter of a circle, or the circumference of a circle.
2 pi r.
2 pi r, right? What is 2 pi? 360 degrees, right? In radians, of course. So this, if you want a marked out portion of a circle, right? Some type of semicircle, you just take the radius and you multiply by the angle it carves out, and that gives you that length. What about here, though? Well, look, the radius, the new radius, okay, is for this delta S prime. What is it? It's actually the rho minus the y. That gives you the radius from O to here, So then I just multiply that by delta theta, and that gives me the delta S prime. Cool. So what we do is we say substitute this expression into here, substitute this substitute this expression up here, substitute this expression here and here, okay, write it all out, do a little algebra, and now we have an expression for strain. It's a pretty simple expression. What does it tell us? It says that if I have a known amount of radius of curvature, as I get farther away from the neutral axis, the amount of strain I expect increases linearly. That's all this tells us. Okay? And this is maybe apparently boring, but this will help us understand how to, or we're going to use this relationship to define deflection. Okay? So if this is our expression that we have. We said that the strain is the ds, or it's delta S prime, right? ds is just like saying, hey, it's even smaller. ds prime minus ds over ds, right? That's the strain. What is ds? We said it's the rho d theta. Okay, what is ds prime? We said it's rho minus y d theta. Okay? Essentially, we're just taking all those deltas that we had and we're just putting d's in front of them. Okay? And we get the same thing. Okay? Now, Hooke's law, we had alluded to it a second ago. That comes into play. The flexure formula, we've also alluded to it a few minutes ago. That comes into play. And what do? We put these things together. Sigma is equal to negative my over I. So we put sigma, put that there, boomba. All right. And then what do we have over here? We have E epsilon. Epsilon is equal to minus y over rho. Right? We have minus, minus. Okay. So those can cancel out nicely. And we're left with a powerful relationship. 1 over rho is equal to m over EI. Okay. We didn't know what rho was a second ago. Right? We said, hey, it's arbitrary. Some radius of curvature. We've now connected the radius of curvature to the moment and to the elastic modulus and the second moment of area. Okay. EI is what can be referred to as flexural rigidity. Right? What does this mean? If you go back to this, right? If I increase EI for a given moment, all right, that means that the curvature is going to go down. Okay. If I increase this, no, the curvature, not the radius. The radius will go down or go up. The radius will go up, but the curvature, which is 1 over rho, will go down. Okay. So flexural rigidity. I'm glad you asked that question. Thanks for keeping me on my toes. All right. So right, curvature is 1 over rho. Right. This is where the kappa came in when you're doing your calculus. And we have these relationships between curvature and stress. If m is positive, then rho is above the beam. Rho is generally large. We already knew this. Okay? So now we have the ability to start thinking about what is going to happen to the curvature. Okay? We need a couple other things, though. Curvature is not displacement. Right? Remember we said we had big V, shear force, not very interesting today. Little v, displacement, very interesting today. But we haven't connected that. We're still missing that connection. Okay? So, right? Remember, this is the little v we're interested in. Okay? And if m is less than 0, we have a rho. Okay? Right? But I don't know how to get this displacement. I don't know how to get this displacement as a function of m. What do? We go back to calculus. And if you want, there's this equation. Does this look familiar? Somewhat, hopefully. You're like, it's somewhere deep down in your database, all right, that you did. All right, and if you don't believe me, Look at Wikipedia, look at Wolfram Math World, pull open your calculus book, okay? You're not going to rederive this here. What is this saying? Okay, this is, and you might have seen it kind of in terms of a dy, okay, not dv, but like a dy, okay, or, you know, second derivative of y with respect to x, okay, as you're going along a line. All right, in this case, our v is the y direction. Okay, and then you have this interesting first derivative, the dy dx squared, all right, in the denominator. Now, we have 1 over rho is equal to m over ei, right? So what you're seeing is, oh, wait a second, I need u right here, not you, I need v, okay? I need little v, okay? And I have now a relationship for curvature, okay? This is curvature, 1 over rho, and I have it related to m over ei. So we can go ahead, equate them, but now I've got this nastiness, okay? Well, guess what? dv dx is really telling us what the slope is, right? Just like dy dx. That's just the slope. And in these cases, we're assuming very small deflections, and we're also assuming that we have very small slopes. Okay? Right? Like if you're bending this piece right here, right? It's not like you see, you know, these curvature diagrams we've been putting up have been quite exaggerated. Okay? So these things, their slopes are typically very small. What does that mean? It means that if this is small, if I take a small thing and I square it, it's even smaller. Okay? And so we cross this guy out of the equation, and we're left with 1 plus 0, and that's nice. So then we only have to worry about the numerator. Now you're like, wait, but you told me that if I squared the small dv dx, it goes away. But the second derivative doesn't necessarily go away, right? And then you can think about that in terms of, oh, hey, look, is it positive or negative curvature, right? And it can be quite high even though the slope is pretty small, at least relatively. So now, what do we get? We get this powerful equation. This is not quite what I would write on your formula sheet, but it's going to be this one that I would write on your formula sheet. Okay? Okay, you guys are smart. I know you are. If I'm interested in getting v, this is the little v, the deflection, and I'm given m, I'm given e, I'm given I, all things that you're familiar with. How do I figure out what the little v is? Yeah, you got to integrate, right? That's what you got to do. And how many times do you integrate? Twice, right? Okay. Now, this is where the number of integrals that you would perform or could perform gets absurd. Look at this. Do you remember this relationship? V equals dm dx. Okay? Guess what? I can take this, take the derivative. If I take the derivative of this expression, what does this become? A third derivative. And what w is equal to dv dx? I can take two derivatives, all right, of that, and I get a fourth derivative. So these are the equations you want on your formula sheet. Do you want to take four integrals? Do you want to do 4 integrals? If you can avoid it.
Get a 100 on the test.
Yes, you'll do it. All right. You're going to try to avoid it. I'm going to try to avoid it. And we're going to show you how to try to avoid it. If someone gives you distributed load, though, all right, so if your problem starts with a distributed force across it, that's what W is, remember? You can go right to this mess and start integrating to your heart's content, okay? Or you can go back here and say, oh yeah, I remember that I figure out what the shear force is, all right? And then I figure out what the moment is. Okay, and I have to do those integrals there, but at least I don't have the EI in front of it. Okay, so it's like, maybe, maybe not. All right, but we're building, so what is true though is that you have to do two integrals once you have the moment diagram, right? So you have multiple ways to try to attack these problems. Okay? And there are going to be even more ways. Oh boy, we are going slowly, too slowly. All right, vertical deflection, flexural rigidity, okay, distributed force, internal shear force, right? That's the big V, not the little v. And then we have internal bending moment. Okay, and let's do an example. All right, so you guys, we like math, right? So here's a math problem with no geometry. Woohoo, right? Yeah, you're like that. Just give me integrals. That would be happy, right? All right. It's like, you know, if you can figure out how to go from the free body diagrams, right, to the, you know, you may think it's overrated, but you signed up for mechanical engineering. So that's what we have to do. All right, we have to go from the free body diagrams to the equations. All right, so here we have an expression where you have the distributed force as a function of x is equal to this minus omega naught, all right, or minus w naught. This is a constant, all right? And then we're going to give you some additional information. When x is equal to 0, the displacement is equal to 0. And it turns out when x is equal to L, some distance L, right, the displacement is also equal to 0. Okay? And then we'll give you a little bit more information that on the left side, whoops, I should not, did I say left side? No, there's no geometry here. Okay, no geometry. When x is equal to 0, the shear force is equal to some quantity. And when the moment, or when x is equal to 0, there's no moment on that side. Okay. What is this? And it's hard not to say what the geometry might be. But you can start to guess what the geometry is. Okay? You could maybe guess. But we're just, for now, we're just going to do math. Okay? Because we all like math. Actually, no, I don't know. All right, so there's one of our equations that we can start with. We're going to do 4 integrals. Starting with just putting in the constant. Okay? What do we do here? We integrate, and then we add a constant. These are indefinite integrals, all right, which makes our life even more interesting. That's why we need boundary conditions. Okay? So we put a C1. We do a little bit more, and we say, okay, this expression is another equation we wrote on our formula sheet. Okay? And I see it's here, and I got to figure out how to get rid of this C1. What do I do? Well, I say I can plug in x equals 0, or I can plug in this expression is equal to this, right? Is equal to negative w naught x plus c1, and I plug in x equals 0, right? And I now have a w naught L over 2. So what is c going to be equal to? Or c1, sorry, what is c1 going to be equal to?
0.
No, not 0. Right?
WL.
Yeah, that's right. Okay, thank you. Okay? So, we do another integral. Okay? And now we have the second derivative of displacement, vertical displacement. We've done the integral. We know what C1 is already, but I just put in C1, but we're going to put in plus C2. Okay? What do we do here? What is this expression equal to? Moment, right? So and we got another undefined constant, so that's equal to the moment. We're going to look at, hey, what's happening at x equals 0? Well, in the moment case, 0. So this time, right, what is C2 equal to? 0. Now we go up again, do another integral. Okay? It's almost cathartic, right? It's almost there. It's kind of fun. This one's fun. Some of them are not fun. All right. We define another constant. We'll call it C3. And what in the world do we do with this guy? This is a little bit weird. all right? Because now we've got a derivative, okay, and we're not quite sure what, like, derivative of displacement with respect to x. If I know something about, this is actually slope, all right, but no one gave me anything about slope here. So what do? Skip and do another integral, okay? And we have here, we have now gone all the way out and we have EI V, right? So if I want the V, I just do 1 over EI times this whole thing on the right. But I don't know C3 and I don't know C4. Well, I do know V at 0 and I know V at L, at x equals L, right? So I've got two unknowns, right? C3, C4, and I've got these two boundary conditions. So I can figure out what they are. The easy one, right, is C4, because I plug in x equals 0. Slightly, maybe more confusing is what to do with what happens at x equals L. I plug in everything, this is the expression I get, and then we solve for C3. Okay? So that's not as straightforward, right? But then, what do we have? We have this wonderful relationship, okay, that gives us the elastic curve, all right? We got to multiply by 1 over EI on that side, okay? But that's the relationship, okay? So what is this telling us? This is, well, this is the geometry that was hidden behind here, okay? If you look at it, right, if you slice it, you do it all out, right, you see that there's a force here, there's no moment being applied there. And the forces are split evenly, right? So that shear force is going to be this W0 times the entire length divided by 2. Okay, that's the internal shear force there. Okay? And like that. Okay? Any questions, thoughts, criticisms about how to do this? Okay, we're just going through now and showing how it's equal. Okay, this geometry is equal to what we just did. Let's keep on trucking. Okay. Okay. When is V a minimum? All right, so you could think of it, when is it the most negative? All right, what do you do there? This is a little bit different, right? You take the first derivative. Well, the first derivative we already solved for, right? Because we were integrating up, right? So this is the first derivative. What do? You set it equal to 0, and if you do that, you'll find that it's at x equals L over 2, right? That makes sense there. Okay, so the opportunity you have here, again, you get to work on a problem that has no geometry. Isn't that fun? Okay, all right. So that's question number 1. Okay, let's go to the second portion and how we go about calculating deflection. Okay, these are the equations. We've gotten some examples that we can kind of intuit what it should look like, all right? And that's important to maintain that mental picture of what the curvature, what the deflection is going to look like. Then we're going to break the beam into different regions, okay, with discontinuities, applied loads, boundary conditions. We're going to look at finding expressions for moment, shear, and or distributed loading, right? So what does this mean? This means some people were upset that they didn't get to draw a shear force bending moment diagram on the last exam. All right, yeah, I know, right? Huh? You weren't upset? Okay.
No one was upset.
No one was upset? No, someone was. They have feelings. They have feelings. I want to acknowledge their feelings. All right? They told me they were upset. All right? So I believe them. All Alright? Just because, this is empathy, right? Just because I wasn't upset doesn't mean that somebody else might not be upset. Right? Just because you don't like this class doesn't mean that someone else doesn't like this class. Alright? That's empathy. Okay? So if we can get to moments, we integrate a couple of times. Alright? 3 times for shear, or 4 times for distributed loading. We had to make sure that we keep adding constants. These are indefinite integrals that have consequences, constants. Okay? And we got to apply the boundary and continuity conditions. And then we're going to think about the slope angle and vertical displacement v. We've kind of alluded to it, but this is an important relationship. The slope angle, all right, is the first derivative of the little displacement with respect to x. Okay? And this is going to be a pain. All right? Let me show you why. You have the opportunity to pick different coordinate systems. And there was, after the first exam, we actually had some interesting discussions. I don't remember who it was with, but I had some discussions a little bit, about, okay, well, how do you define your coordinate system along a beam? And if you do it this way, this is how I would prefer to do it if I was just a glutton for doing a bunch of math, okay? If I just, I'm going to do my first break and my second break, all right, where I have my x1 and I just keep breaking things, I just look at the slices, all right, I do it this way. If I'm thinking a little bit more about geometry or a little bit more about graphical methods, okay, and trying to cut some work out, okay, I will probably think about going and having systems from either side, okay? This is another way that you can do. So you have multiple, you have 3 options here in terms of how you define the coordinate systems across the beam. And what you can see is that you are going to be looking at these coordinate systems and trying to make sure that you have appropriate ones as you get through different sections. It's like surfing. Any surfers here, right? I'm not a very good surfer, right? But you're going along and you're hoping that you have enough speed so that you don't get knocked over by the wave, okay? If the wave is still going. So you have to get through one section to get to the next section, to get to the next section. So as you get to different sections, you have different coordinate systems here, okay? So we have to keep track of our conventions that we've discussed previously. Very important here, okay? Very important, okay? So, if it's coming out of this direction, V going that way. If it's coming out this direction, V is going down, okay? We also have to keep track of the slopes. This is why it's a pain, all right? Look, this is a positive slope coming from the left, right? Does that look like a positive slope that's really happy? Okay. If I go from the other direction, my x, this is also a positive slope. Okay. What happens though, okay, is I will think about using coordinates from the same direction, and then this is valid, all right? So if I'm at a particular D, right, away here, right, I'll be at the same point, right? V1 of D is right here. V2 is also right there, okay? Okay, all right. If I go from opposite sides, all right, then I get V1 of D, all right, is here, or here. And V2 of L minus D is also here. But guess what? See this? If the x1 and x2 are coming from the same side, then the slope, if it's positive coming from this side, it's still positive, okay? But you see the curvature, if I come from this direction, right, I've got to actually put a negative in front of it. And this is the pain. This is the pain, okay? And this is something to keep in mind. So if you're coming from this direction, then the slopes end up being the additive inverses of each other. Boundary conditions. They're going to affect all these parameters that we care about. The shear force, the bending moment. You already know this though. So if they affect the shear force and the bending moment, or if they affect the bending moment in particular, right, we know they're going to affect displacement. And we know it's going to affect the theta. So if you have a roller or pin at the end of a beam, the boundary condition is that the displacement is equal to 0 and the moment is equal to 0. There's force though. There's transverse force there. If you have a fixed end, all right, the displacement is 0, and guess what? This is a cool thing about, this is like maybe one nice thing about a fixed end, is that the slope coming out of that wall is horizontal. Okay, so you can use that relationship, this one, at the walls. If you have a free end, then the shear force and the bending moment are going to be equal to 0, okay, which is nice. All right, but it doesn't tell you exactly, okay, it doesn't tell you what the little v is, right? Remember, little v displacement, big V shear force. Okay. So here we have another example, and we have a general idea for the curve. That's one thing that we do. We break it into two regions. We have x1 and x2. We are able to write out a shear force diagram, and we're also able to draw out a bending moment diagram. Okay? And that, if you want to go back, you can review that. What do we do from here? Well, we can now write out expressions for moments. Okay, do you see this? This is a little bit weird because we have x1 like this and x2 coming from this direction. They both have positive slopes, even though this is a negative slope, right, if you're coming from the left side. So we do some integration, right? What do we integrate? We have our equation, EI, second derivative of v with respect to x1 is equal to m. And we can write out the integral, for the one integral. We can solve, right? Or do another integral. Okay? And for x2, we can also do the same thing. And don't use the same c1 and c2, but write out c3 and c4. Okay? What are the boundary conditions? Well, boundary conditions at the left side, right, we have it equal to 0. At the right side, we have it equal to 0 as well. And you know, if we want to be sneaky, we could say, oh, actually, I also know at L over 2, okay, that this slope is 0 because of symmetry. Be very careful. This has come back to bite me, though, on the problem that you guys will get to do. You folks will get to do, right? So C2 and C4 are equal to 0. And with continuity, we have at this location V1. This is true, right? V1 and V2 at this midpoint, those are going to be the same. Okay? And this, you got to be careful. The angle, all right, on this coming from this direction, okay, is going to be the negative, the angle coming from this direction. And so then we can go ahead and we can use these relationships, all right, to solve for C1, C3, okay, and we can then write the complete expression for the elastic curve for x less than L over 2, right? And then if we want, we can write the flip for like an x2 coming the other direction. Okay. An alternative approach, okay, is to use symmetry, all right? And we can say that theta 1, okay, is equal to theta 2 is equal to 0. So again, be careful when you do this. It's true, okay? And so if we do that in this case, right, it bottoms out here. That's kind of nice. Just be careful, okay? Then we can solve for C1 and C3 a little faster. And we can once again write this expression, okay? All right, so the second question, this is harder than it looks, okay, to be honest. harder than it looks, all right? And actually, there's a nice little thing that we did in the office hours. One of your classmates came in and said, hey, this question is hard. Last office hours, they were ahead, okay? So now, essentially, the problem is almost done if you look at the Session 24 OneNote notes, which you can find on the website. Okay? It's not quite done. There's still some algebra that has to be done, but at least the principles are there for you to finish it off. Okay? Great. Oh, and actually, I posted the solution. Oh, shoot. Okay, it's done. It's done. It must be posted then. Good. All right. The last thing we're going to do, and very quickly, okay? That was an accident, but that's a good one for you. All right. The last one that we're going to do is looking at deflection using finite element analysis. All right. And you're like, can you really do it this fast? Yes, I think I can do it this fast. I think I could do it in 6 minutes. All right. Okay. So what you're going to see their tables, and you should go through this actually. All right. So there are tables that we will talk about more next time. Okay. And these tables are essentially the shortcut. Like they did all the hard work for you. You can figure out, they just plug and chug here. But just be careful because they use different sign conventions. So I wrote beware or it's copied 3 times. But as you know, many of us will use finite element analysis. Okay? So we're going to try to do that. Okay? We're going to try to do that here. And you're going to get to do this for your homework. All right? You have slightly different geometries. Okay. So what do we got here? We have a beam with length. Oh, you can't see this. Oh, this could be interesting because I'm not sure if I'm good enough. All right, I'm going to try though. Because we've got this thing. Okay, yeah, I'm not sure if I'm good enough, guys. Maybe I won't be able to do it in 3 minutes or 6 minutes. Okay. All right, so we're going to open up FreeCAD. And I'm going to drag it over once it's open.
Professor,
Yes?
can we do this on SolidWorks?
I would prefer that you use FreeCAD. That's what I'm going to say. I'd prefer. This is not hard. This is super simple. Okay? We create new. Okay? We go over here, and you can watch the video if you don't like this one, all right, that I've already prepared. And we're going to use part. Okay? We go in here, we put the cube. Okay? And it's a box. It's going to be 1 meter long. Whoops. 1 meter long. I think it's, what did I say here? 0.2 meters wide and 0.1 meter high. Okay? 0.2 wide and 0.1. Yeah, that's right. Okay? Uh-oh, no. All right. It's 1 meter, not 1 millimeter. Okay, now we got this. So that's about as fast as you can create a geometry in any CAD program. We go over here and we move to FEM. All right? And you can then start your analysis. So you create what's called an analysis container. And we have here the building of an analysis here. So you go over here. This is, for better or worse, this is the material. That's not an intuitive shape for me, for what the material is, but it's beautiful. So I'm going to use aluminum generic. That's going to give me the 70 gigapascals. I hit OK. All right. And then I come over here and I'm going to add a constraint, a fixed constraint. I'm going to fix this side right here. Okay. So I'm going to click add and then I'm going to fix that right there. Okay. Over on this side, I'm going to add a force. There's a force, they call it constraint force right here. Okay. That's the side. So I'm going to hit add and then I select this side. I want it to be 1,000 newtons. But look, this would just be the bar coming out. right? What we want to do is we want it to be in this direction. So I can select an edge, hit direction, and I'm going to put reverse direction, and then I'm going to hit OK. Okay, you see that? Now it's coming down. Isn't this nice? Now, this part you probably can't see because there's sometimes a thing here. So I'm going to move it down a little bit so that you can see what happens. All right. So in this part, what we got to do is we got to come over here. Whoops. And we've got to select the cube, and we've got to do the mesh. Remember how to do mesh? Here we're going to make this 20, and we're going to do this fine, and we're going to hit OK. And it's going to take a second. Whoa, okay, so you see now we got a nice little mesh. Okay, see that mesh? Great. Then we come over to the solver inside here, under analysis, click on solver, okay? And we're gonna come over to this one right here. And we're gonna run the solver calculations. Okay, I got a minute left. Okay? And once it's solved, all right, I can click on these results right here, okay? And I can click on displacement, like that, all right? And it tells me that my maximum displacement is 219 nanometers. Okay? Guess what, though? That's the max, that's a positive number. The one I want is the minimum, actually, because it's negative z. So it's 0.28 millimeters. All right? And that's the same thing, 0.28 or this is minus 0.29, okay, millimeters. It's 286 micrometers. That's pretty close. Okay, you can watch the other video that's already up there, okay, but that's finite element in about 5 minutes. Thank you, everybody. All right, I'm gonna go ahead and do the favorite part for everybody here. Okay. Just like there. All right. And if you have any questions, I can stick around for a few minutes to go through things.
Can you update
Thank you.
please?
What's that?
Can you update roll, please?
Update. Oh, yeah, well, yeah, we need to do that still.
Thank you.